So, the topic of discussion here, the goal is to understand horizon pressure. This is a pressure that I found was actually hidden in the Friedman equation. Um, it's the fundamental equation of cosmology, basically explaining the universe's expansion. It was found 6 years after general relativity, so 103 years ago. This is the equation. You don't need to understand all of it because obviously there's a lot going on. It looks intimidating. But for our purposes, it's actually somewhat simple, as we'll simplify it here. But the main point is that this term, this h squared, represents the expansion rate. That's how fast the universe is expanding. This is a constant that we don't need to fully dive into. This is the energy density term right here. That is the main term we're going to be looking at. And this term right here just represents intrinsic curvature. Not necessary to fully understand it. One, because this k term for our universe is zero, meaning it's flat, or it's very close to it, but for all practical purposes, it's flat. So this term would become zero, but we're going to keep with it, or keep it in just for generality. Main point is that because this is zero, or this will be absorbed into the radius, these are the two terms that we're looking at. So basically, h squared is related to the energy density by a constant, meaning that the higher the energy density, the faster the expansion rate. That makes sense if you think about it like early stages. Universe was super small and dense, meaning a higher energy density and faster expansion. So we'll clean this up a little bit for what we're trying to get at, and we'll start by moving this term over to the left-hand side. And this is now the exact same equation, but this is over here. We will then divide both sides by c squared. The reason for doing that is this term now actually becomes the inverse radius squared. Definition of the radius is just that, so that term now becomes this, simplifying things a bit. This term now shows pretty clearly, or this equation, how the energy density multiplied by a constant causes the overall curvature of the universe due to the radius squared. The energy density is related to the radius squared. We can simplify it further. Let me explain that first. We can just move this 3 up top here, this 8 pi g over here, and our equation becomes this, and we are now solving for the energy density. The reason we're doing that is because now that we can see how the energy density definition comes from the Friedman equation, we recognize that by definition, energy density is energy divided by volume, so energy density multiplied by volume gives us the energy. If we multiply the energy density, this term right here, by standard definition of volume of the universe, that all simplifies to this thing, which is pretty neat. So now we have a simpler constant multiplied by the radius gives us the energy. So what we find is the energy of the universe is represented by a constant multiplied by the radius. Basically what that means is as the radius gets bigger, the universe grows, the energy is bigger as a result, or they work together, all multiplied by this constant. Now, what that means is that because this is constant, as the radius gets bigger, this little d right here is essentially the derivative of the radius, meaning a small change in the radius is equal to, or results in a small change in the energy. This term doesn't change because it's constant, so this is a bit of calculus. You don't have to understand anything underneath it, but essentially because this is constant, we can see a change in the energy is equal to a change in the radius. From there, we can reorganize that. We can move that dr, change in the radius, to this side, and this gives us a change in energy over the change in radius, the radius being a distance. That's the standard definition of a force, actually. So what we see is this c4 over 2g that we have is a force. Now, that is interesting because actually we can mechanically check that. So interestingly, from Newtonian physics, the simplest definition of force, the mechanical definition is the mass times the acceleration. And for a system like the universe here, the acceleration is actually the surface gravity. It's the acceleration at the outer horizon of the expanding universe. What we can see is the surface gravity, the definition for that from the universe, called an FRW universe, one that we live in, is c to the fourth over 2gm. If we multiply these by together, the masses cancel, and we've confirmed through two different definitions that what we have here is a force. So we have this force acting, and when we think about it, it's the mass times the acceleration, but that acceleration, or that total force, isn't over just a single place where there's an acceleration, but it's actually distributed over the entire horizon. So what we can do is then divide all of it by the area, because that force is distributed over the area. This is super interesting because we have to do it to each term, but the area times the derivative of the radius, so think about it again, is if you have a boundary, the area of the horizon, and the radius increases a little bit, that's actually an increase of the volume. So the area times the derivative of the radius from standard mathematics gives us a change in the volume. Now the force divided by an area is a mechanical definition, just like the one we had for force. Force over area is a mechanical definition of pressure, and this is the derivative definition of pressure. So the change in the energy over the change in the volume is pressure. And because those two definitions check out, we can then see what the pressure is of the cosmological horizon just by doing this quick algebra. And we see that we have c to the fourth over 8 pi g times the radius squared. Spoiler alert, that is the cosmological horizon pressure, and actually completes the first law of thermodynamics for the universe. Pretty wild. Earlier we saw that the definition of the energy density of the universe from the Friedmann equation is this right here multiplied by 3, so we can see that the pressure is actually a third of the energy density. What does that mean? Well, if we know that this term right here is correct, that means the change in the energy is equal to the pressure times the change in the volume. And we have a famous result from Stephen Hawking and Gary Gibbons from the 70s, I believe, that shows that a change in the entropy, which is a thermodynamic term, multiplied by the temperature gives us twice the change of the energy. So the question is, what is the other, if we know that the universe gets bigger, the energy increases, what is the other dE, the other derivative of the energy that's involved? Well, we just found that an increase in the energy results in a work term, this pressure times the change in the volume. So if this term is 2 dE and this term is 1 dE, then that gives us this, the standard first law of thermodynamics. That's how it works for the entire universe. So this is typically seen in standard classical thermodynamics, how engines and all the typical examples work, and hidden in that Friedmann equation, which we just saw through completely standard mathematical manipulations, gives us a pressure, which completes the first law for the universe. Lastly, because of that, or because of this definition here, that the pressure is equal to a third of the energy density, just to show that it can be done, we can rewrite the Friedmann equation as h squared with this p term rather than this energy density and this 3 in the constant, which was somewhat mysterious earlier. But now we can see that the equation that explains the expansion of the universe actually shows that it is a pressure, whether you want to call it driving the expansion or just the simplest way to explain it is the bigger the pressure, the higher or the faster the expansion rate, which is essentially intuitive and how typical pressure and expansion works in thermodynamics. So there you go. From the 1922 Friedmann equation right here, we were able to derive a pressure that completes the first law of thermodynamics and lets us understand expansion via pressure. Hopefully that all makes sense. It's all accepted definitions, all accepted physics. Equation heavy for someone who isn't used to it, but I think just through following the algebra and a touch of calculus, you can see how it works. But maximally simple, interestingly, or I should say importantly, each of these terms in the first law, so the pressure, the volume, the temperature, and the entropy are all completely based on the radius, as you can see here. So it's a completely macroscopic pressure, as the temperature and entropy are as well. The huge finding of Hawking and Gibbons is that the entropy and the temperature are defined completely on the cosmological horizon. One of the very interesting things in horizon thermodynamics and in cosmology, that they are based on everything happening inside of the bulk, as it's called, inside the volume, but they have their own properties due to the craziness of how cosmology and horizons work. So this pressure term completes that, because even though it is dependent on the energy density inside of the volume, the entire, it's horizon based for the first time, because we have the force divided by the area, which is a horizon quantity. So the first law of thermodynamics for the universe is sourced by the bulk or the volume properties, but the entire description is essentially horizon based, and this completes it for the first time. So there you go.